So how much I'll get if I multiply? 4 into 4 is 16 minus 1 into 12, right? Next, minus 4 plus 3. After this, 12 fours are 48 minus 36 minus 12 plus 9. So how much we have? We have 4 minus 1 and then 12 minus 3. This implies, what do I got? I got a square is equals to a. Therefore, the matrix A is idempotent matrix. Clear? Understood? Right? Next, all properties we write at the end. Second type we will go. Second type is invalidatory matrix. Copy this one and put that in invalidatory matrix. Can I scroll up, my dear students? Second type in this is invalidatory matrix. LUTORY. So in invalidatory matrix, you write the same lines, a matrix, a square matrix of order n. If A square is equals to identity matrix. So one example here. You take matrix A is equals to 2, 3, minus 1 and minus 2. 2, 3, minus 1 and minus 2 is an example for invalidatory matrix. If we are calculating A square in this, 2, 3, minus 1, minus 2, 2, 3, minus 1, minus 2. Two twos are 4, minus 3, 2 threes are 6, minus 6, minus 2, plus 2, minus 3, plus 4. So how much is this? 1, 0, 0, 1. So A square is equals to identity matrix. That means the matrix A is invalidatory matrix. So identity matrix is both idempotent and invalidatory as well. Clear? So now the third one, nilpotent. Nilpotent matrix. Here O stands for null matrix. A square matrix of order n is said to be nilpotent if A power n is equals to null matrix, where n is a natural number. Clear? So like here, the smallest value of n is index of the nilpotent matrix. Example of nilpotent matrix. Identity matrix cannot be nilpotent matrix. You can take null matrix as an example if you want. This is an order 2 nilpotent matrix. So if I do A square in this, zero, row 1 multiplying column 1 0, this is also 0, all 0. So I got A square is equals to 0. This implies it is a nilpotent matrix of index 2. Clear? So next, the fourth one, periodic matrix. Similar to a periodic function, this is periodic matrix. We know every matrix A power 1 is A only, but like we cannot say that matrix as periodic. That's why A power K plus 1. K is some natural number. K can be 1. Right? You take idempotent matrix, A square is equals to A. Idempotent matrix is periodic. And then again, as we seen in functions, the smallest value of K is period of the matrix. You need any examples you can take. All idempotent matrices are periodic matrices. So if I say like all involuntary matrices are periodic matrices, you guys will agree with me? All involuntary matrices are periodic matrices. You guys agree with me? True. Write that one as well. All involuntary matrices are periodic again. And in this case, the period is 2. Normally A square is identity. Multiply A on both sides. You get A cube is equals to A. These are all the basic 4 types of matrices, right? Now we are going to see those matrices properties one by one. Clear? So before seeing those matrices properties, I just want you to try this problem. This is a problem from the book only. You go step 3 somewhere in matrix matching, it will be there. I didn't remember exactly which matrix matching and which page. You can find this problem. This you can see as a matrix matching in our book. In this matrix matching, column number 1, I hope everybody copied this. I'm moving up. So in this matrix matching, they have given like in one column, all order 3 matrices. In second column, they have mentioned the names. Nilpotent of index 2, nilpotent of index 3, invalid 3, idempotent. So you should know the definition of these all matrices, then you can solve this. How to do that? Take A, find A square. If A square is equals to A, then it is idempotent. If not A, then it cannot be idempotent. Not now, try at home. It takes time, matrix multiplication, no? Right? See, like I'm giving you the hint. Every matrix, you call the matrix as A or M, whatever alphabet you like, do A square. If it is equals to identity, mark for invalidity. Not identity, you keep like maybe some matrix A square is equals to null matrix we got. That is nilpotent. Clear? So if it is not coming, that cannot be nilpotent of index 2. Then find A cube. Why A cube? They only wrote here. Nilpotent of index 3 or nilpotent of index 2 only we have. We don't have anything other than this. So what you need to do is A square and A cube you need to find. A square is equals to A, that is idempotent. A square is equals to I, that is invalidatory. A square is equals to null, that is nilpotent of index 2. If not, that will be nilpotent of index 3 as per given. Clear? Try at home. Now we will see the properties of these matrices one by one. Maybe you can say in this properties, we are including few problems as well. If A is a idempotent matrix, so before I am solving, I would like to give one attempt for you guys. Try once. They have given like if A is idempotent matrix, then B is equals to identity minus A. That is also idempotent matrix. We need to show that. So how are we doing this? Anybody from online? Squaring on both sides. Perfect. He did it. That's why he knows. Like squaring on both sides. Or else, like first of all, A is a idempotent. So we can say that A square is equals to A. Name this one as 1. Given that B is equals to identity minus A. To show that B is a idempotent matrix, I need to prove that B square is equals to B. For that, squaring on both sides, B square is equals to I minus A whole square. Like in matrices, normally you cannot apply the formula if you say A plus B whole square. You cannot write A square plus 2ab plus b square unless until a and b are commutative. Right? See, like here I don't have a and b, I have only a and identity. Matrix multiplication with identity is commutative. So I can write here, this will be equals to I square plus a square minus 2a. I square is I. From equation 1, a square is a. This is minus 2a. So I got here I minus a, which is equals to b. B square is equals to b. Therefore, B is idempotent matrix. Am I clear? Right? So second one then. I'm scrolling up. I hope everybody copied the statement. Yes, please. If A is a idempotent matrix, then I plus A whole power n will be equals to I plus everybody copied no the previous one. So like here, nothing much. We use the definition of idempotent. A square is equals to A. If A square is A, what is A cube? For that, multiply with A on both sides. A cube is equals to A square, which will be A itself. Right? Now, multiply with A on both sides for this. A power 4 is equals to A square, which will be A. Now, similarly, a power 5 is also equals to a square, which is a, and so on. You can prove that. If a is idempotent, in that case, a square is equals to a cube is equals to a power 4 is equals to a power n is equals to a for all n is greater than or equals to 1. If n is 1, a is a only. No. If A is a idempotent matrix, I can use this. A square, A cube, A power 4, and so on going till A power n is A itself. Clear? Now using this, let us expand I plus A whole power n using binomial expansion. This is NC naught I power n, which will be I only, plus NC1 I power n minus 1 into A, which will be A. Multiplication with any matrix with identity matrix is the matrix itself. Clear? Next you will get plus NC2 into A square plus NC3 into A cube plus and so on. We are going till NCN into A power n. Right? Now I am substituting the above result. NC naught is 1. So I plus NC1 into A, NC2 into A, NC3 into A, and so on. It is NCN into A. There is A common, take that out. I plus NC1 plus NC2 plus NC3 plus and so on going till NCN into A. So what is the value of this bracket, my dear students? NC1 plus NC2 plus NC3 going till NCN will be equals to how much? In a binomial theorem, you would have learned sum of all binomial coefficients in the expansion of 1 plus x whole power n is equals to 2 power n. There is no NC0, that is 1. So we should subtract it. This will be equals to I plus 2 power n minus 1 into A. Am I clear? Copy this, please. One 180 factorial must be a big number. Copied? Any doubt in this? Anybody? Then third one. So in third one, please listen. Trace we didn't discuss yet, right? We didn't discuss trace. Then about trace we will write in trace only. We didn't know about transpose and all, right? Trace and transpose we didn't know. Think then this two will do. Remaining is about trace and transpose. Let me see, there are some problems like this in step 3, where they'll say one is idempotent. We should find. If I am not wrong, page 30, 17 problem is a problem on idempotent. I don't have any problems. Like remaining are properties on trace only. If we don't know about trace, we cannot write them. I think earlier I have mentioned identity matrix is both invalidatory and idempotent as well. That is periodic again. So then we will see the trace of a matrix. I lost the count. I think 6 is product of matrices. 7th one is trace of matrix. Correct? I have given list. I didn't remember what is product of matrices number. Can you check in your notebook? 7th is trace of matrix. Now we are doing 7. Trace of a matrix. Trace for every matrix is not defined. Trace is defined for a square matrix. The sum of principal diagonal elements of a matrix A is called trace of a matrix A. See, trace of a matrix will denote as TR and matrix A. trace of matrix A will be equals to with the help of summation, sigma I is starting 1 going till n, a I. So like without the summation, that will be a11 plus a22 plus a33 plus and so on a Sum of all principal diagonal elements is known as trace of a matrix. If you need one example, let us take A is equals to 1, 2, 3, 4. For this matrix A, only one principal diagonal will be there. Trace of A is equals to 1 plus 4, that is 5. If we take any order 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 5, 9 are principal diagonal elements. In that case, trace of A is equals to 1 plus 5 plus 9, which is 15. Trace of a matrix is a scalar quantity. It is a scalar, it is not a matrix. You observe addition of two matrices is a matrix. Scalar multiplication of a matrix is again a matrix. Product of matrices is a matrix, but trace of a matrix is a scalar. It is not a matrix. Clear? So now we should see the properties of trace. Some basic properties we should know. Right. So like how this trace exactly works and then how to do when we have 2 in addition, 2 in multiplication, something like that. Everybody copied till here? Understood what is trace of a matrix? Sum of all principal diagonal elements. So in this basic properties, first one you can write here is trace of a identity matrix of order n is equals to n. If it is an identity matrix, we have only principal diagonal elements all are equals to 1. I am adding 1 n times. That's only n. Trace of identity matrix of order 2, that is I2 is equals to 2. Trace of identity matrix of order 3, that is I3 is equals to 3. Now, if I am taking any empty matrix or null matrix, trace of matrix on stands for null matrix of order n, square matrix it should be 0. Trace of identity matrix is n, trace of null matrix is 0. Don't get confused, small o is 0, capital O is null matrix. Now I can say trace is distributive over addition and subtraction as well. Let's say two matrices are there. For the trace of A plus minus B, I can write as trace A plus minus trace B. You take any two matrices, you are adding them or you are subtracting them. You want to find trace, no need to find for addition, you can do individually and add or subtract there. Trace is distributive over addition and subtraction. Like I can also say trace of scalar into a matrix is equals to scalar into trace A. Scalar can be taken out, scalar won't be affected for the matrix. Clear? Understood? Right? Now, in general, if I write linear combination, we will be having, let's say, trace of A1 plus K2 plus K3 and so on going till Kn An. Linear combination of n matrices and n scalars. In that case, I can write this is K1 into trace A1 plus K2 into trace A2 plus and so on Kn into trace An. So I can relate this one to differentiation and integration. Constants we can take out. Clear? Now the fifth one, trace of a power n is also equals to trace a whole power n. Trace is non-distributive over multiplication. Trace of AB is equals to trace B into trace A. Trace is non-distributive over multiplication. In general, if you have n matrices, trace of A1, A2, A3 and so on going till AN, that is trace of AN into trace of AN minus 1 and so on, trace A. Some doubt here, online student?
That is seventh one, sir. You wrote 6.
Okay. Count mistake. Thank you for reminding. So then 5 minutes is there. Let me mark attendance. Right. Please try those sums what I have mentioned as homework. If you solve those sums, I'll teach something new. I won't teach them again. Clear? Online students, please respond to the attendance call. If your name is there, please unmute yourself and respond. Arish S is there. Arish S. What's your name? Mohammed. Jagdish VR is there. Jagdish VR. J. Sarvanan. Yes, Gautaman. Tanish. Tarun Krishna GP. Vinota R.
Yes, sir.
Oh,
Sir,
Vinota R
Tarun
is
Krishna
present.
Prashant.
One moment, please. Tarun Krishna G is also there, not responding. Yalini is also there. So then, one moment, please. Aditya K is there online. Please respond. Aditya K is there online. Arish, yes, is absent. Afa is there online. Yes, online. Ajay Andrews. Okay. Ajit V. Akhilesh, yes. If your name is coming, you can. Arun Bharati KA. Gugan, yes. Hariharan J.
Yes, sir.
Hari Krishnan I.
Yes, sir.
Harish M. Harish Kumar S.
Yes, sir.
Harivarshan, yes. Jivi is there? No, not there. Jiva Taran. Okay. Joshia Moses. Kirti Sri.
Present, sir.
Loga Prasanna Ganapati. Lohit. Mithun, yes. Mohammad Saifuddin Amir. Muthu Selvam T. Muthuvel. NS Ajay Khanna. Naresh Balachandran. Nakshatra SS.
Present, sir.
Padma Vinita V.
Present, sir.
Pranav Lakshman MG.
Present, sir.
R. Sai Nitin Pandi. Ritika T.
Present, sir.
Roslyn. Sabrinathan. Okay, Sai 7. Santosh, yes.
Sir, Aditya present, sir.
Sorry?
Aditya present, sir.
Okay, boss, I marked present only. I didn't mark the absent, don't worry.
Okay, sir.
Shiva Ganesh M is there. Shiva Kumar S is there. Shiv Santosh, yes? Okay, mark. Sri Hariharan S.